All right, I am Dr. Rachel Traylor. I founded the Math Citadel, which as of right now is a little bit half math blog, half repository for all of my research. And the talk that we'll basically look at today, I titled The Gravity of Mathematics for a reason. A lot of things, of course I'm not that old, but industry used to contribute a lot of really heavy mathematics, certain things that honestly would make the storage industry impossible without. Bell Labs in particular was one of the major contributors for this. That kind of died. So the goal of the talk is, one, to kind of talk about why it shouldn't have, how to bring it back, why you should care, because it's math, and go back to academia, right, for all I care, right? You know, that's where you belong. I disagree with that fundamentally. And then I'll basically illustrate that with some examples of some of my own research I've done between the time I started my dissertation and now, both heavily theoretical that may not have applications yet, and stuff that's very clearly applicable. So that's the goal here. So the first one is just to actually note, these in particular are specific industry contributions to mathematics. And this is for theoretical mathematics. This isn't computer science, this isn't data science, this isn't machine learning, this is math. Not the same thing. So the student's t-distribution, everybody knows that one, right? That's essentially how you handle the idea of small samples when you can't use the normal distribution. It's a bell curve. It was created by Budweiser, a statistician at Budweiser who wanted to publish it, wasn't allowed. He published it under a pseudonym. But he did it while working in quality control for Budweiser.
Did not know that.
Didn't know that.
Taguchi arrays are heavily important in manufacturing experimental design. Experimental design is one of those fields that, because of some of the advances in mathematics, the analysis of well-designed experiments is literally as easy as high school statistics and guaranteed to be able to show you where all of the variance can be broken down. So is it due to the thing I tried to affect? Is it just random noise? You can actually break those down. Taguchi arrays were actually invented by a Japanese engineer, and I don't remember which company he was working for. It actually took mathematicians 10 years to explain why it worked so well. But what it handled was the notion of, if you have all of these features you want to do an experiment on, say in a manufacturing process, and not very much time to test all of them, or money, right? Some tests are destructive, so you don't have the money. How do you select the subset of possible combinations for experimental runs such that you can still guarantee the type of analysis you want? That's what that problem solved, provably. Statistical process control, information theory, queuing theory, error correction codes all came out of Bell Labs. Statistical process control led to your Lean Six Sigma. That's all the math behind that. Information theory and error correction codes, since all of you are in storage, are probably something you are intimately familiar with, invented by Bell Labs and invented by mathematicians. Queuing theory, which actually was one of my research interests, or still is, also invented by Bell Labs. That allowed things like traffic control. Traffic control for shipping, traffic control for cars, traffic control for just about anything, including continuous flow in an electric grid, invented by Bell Labs. All that mathematics was invented by industrial mathematicians. On the other end, these are, not everything that was invented in industry mathematics. There's still contributions that came out of the academic side that also played a huge role in application and development. So experimental design, I brought that one up again because, again, a lot of the stuff in manufacturing quality, how to actually optimize the type of testing you need to do so that you can test what you need to test without spending more money than you have to or destroying more products, right? If you're trying to do fatigue testing and you have to destroy things, you want to do that as little as possible. So how do you basically optimize that? Reliability theory, that's actually a specialty of mine. That's what governs, for instance, say Lockheed's maintenance logs. When should they check and replace parts, right? You don't want to wait till they actually break. You want to figure out when they're going to break and when to check them, because sometimes taking apart half of a wing is a pain in the ass. So you need to figure out when you want to do that. And if you want to do that, you're going to model both components and systems. That mathematics, again, the mathematics allows this to happen. Boolean algebra, duh, you're all in computers. Ito calculus.
Enough said.
Ito calculus is
you either get it or you don't.
Yeah.
Well, remember, there's only 10 kinds of people in the world.
Yeah, best. Yep, there you go. Insert your Boolean jokes here with whatever probability. Ito calculus is an extension of standard calculus. What this allowed was the concept of white noise. So the concept of white noise is a random process that is everywhere continuous and nowhere differentiable, which means you can't integrate anything with respect to it. If you can't integrate anything with respect to it, how are you going to handle modeling stuff with lots of noise? That branch of calculus was invented, and it's actually the underpinning of most of the automatic trading algorithms in finance now.
Am I the only one that's disappointed that that's not LTO calculus?
You wanted LTO?
Yes. You're very
Yes,
sorry.
it is. It actually, you are the only one. Yeah.
Yes.
Group theory.
She's like moving right along.
Am I too young to get the reference?
No, LTO is a tape technology.
See, mathematician, like, this is what I get for presenting to storage
Okay,
people.
you know what counts.
Yeah.
Oh.
I don't know most of what you're saying, so it's totally fine.
Group theory. I love you, group theory, and also hate you. Algebra is not one of my strong suits, or abstract algebra. The thing in group theory is you can actually go through a lot of examples of how this actually impacts mathematics, but probably one to kind of diversify its reach is actually in pharmaceutical drug trials. A lot of times you want to simulate the interactions of some of these drugs with proteins or what have you, but you want to cut back on your animal testing. So if you can actually synthesize the drug virtually and test it without having to actually physically synthesize and run it on an animal or whatever, group theory allows you to do these syntheses and actually know what molecule you made. Is it this? Is it a chiral version? Handedness, right? Your hands are chiral, meaning they're mirror images, but I can never superimpose them. So a lot of the stuff that's underneath group theory explains a lot of molecular theory in chemistry. Backstory, I almost have a bachelor's in chemistry.
So I have some friends that are doing virtual twins for technology, and they might be using group theory. I don't know.
Probably.
That should be interesting.
Even if not, they're probably using it implicitly.
Yeah.
Fluid dynamics, not too many engineers in the room on this one. I feel like that's pretty self-explanatory, right? It's how your airplane flies. It explains how your airplane's going to fly. It explains how your boat's going to cut through the water. It explains how to design a speedboat that makes water skiing super fun. Obviously, there are tons more examples, but a lot of the complaints that I see floating around the Twitterverse or what have you about who cares about funding mathematics? Why do we care about this research? Besides the fact that no one's going to care that I just think it's beautiful and worth doing, if I'm trying to explain to you why it is worth doing, because these developments would not exist without the mathematics underneath it.
I looked up Taguchi arrays, and it was NTT.
NTT is the company?
Yeah, from Japan.
Thank you.
You got it.
Yeah, it was interesting that it took mathematicians a long time to actually go underneath and figure out all of the theory to explain and prove why they were so successful.
Also known as orthogonal arrays.
Orthogonality is your favorite thing in mathematics if you can have it, for anyone who's a data scientist in the room. I'll actually come back to that orthogonality concept later. So hopefully that's at least giving you some kind of, math is actually useful and not just to kind of torture your kids with in school. Why should we rekindle this relationship? It died. Like, no joke, it died. Name a major company that funds a math department today. I actually tried to get that to happen and failed miserably.
Don't stop trying.
I'll keep trying. I keep trying for myself as well. What's the usual complaint I get? We work slower and can't be put on a development cycle. I can't guarantee you a paper in 2 weeks. I can't guarantee you results every 2 weeks. I can't guarantee you pretty pictures. I can't guarantee that I will have a result in a year, but I will try. In fact, what may happen is that I will beat my head against a wall for 3 weeks and then come back and say, well, it didn't work. I found a counterexample, the theorem's not true. And then you're like, great. So not only is it a theorem and I can't touch it or do anything with it, but it didn't work. That sucks. However, what do you get out of it? These days, the conversation around machine learning is starting to change a little bit. People are starting to have ethical, moral questions about these black box algorithms that are floating through a lot of companies. So what's the problem with it? You can't explain what's going on underneath it. It's impossible. Why? There's no mathematics to handle it yet. We'll go into it.
I have a counterexample, but please go ahead.
Counterexample.
She
There
hasn't
is
given an example
mathematics to fix that, and there's a company doing it right now.
What company's doing it?
Optimizing Mind. It's the name of the company. It's a small little startup in Palo Alto. They have solved the black box.
Then Optimizing Mind and I need to talk about my research.
Yes.
There you go. Opportunity.
So what do you get out of it though? Machine learning algorithms, yeah, I can do a deep neural net and have one up and running for you and spitting out results a whole lot faster than letting me take the time to study, fuzzy sets and look at time series modeling based on that, because that'll take me a couple of years. What do you get out of it? You get elegance. That might come back to my notion of I like beautiful things. But the nice thing about elegant models is they don't require tons of data and tons of computational power. I'll talk about an example of actually how that proved out in my own research. Interpretable models. One of these days, the regulators will come calling for your company and your analytics, and you're going to be dragged into court to explain why you denied that person a loan. And if you can't explain it, they're going to make up an explanation and you're going to get hit with fines. If you don't have an interpretable model that explains what's going on, you're going to end up in trouble. Generalizable solutions. Most algorithms, you set them on a data set or a type of, some space of data sets. You set it to run, it keeps learning or what have you. Now the problem changed a little bit, slight twist. Either it takes time to adapt or you have to start over, create a new neural net to learn that data set. Generalizable solutions, something that can apply across multiple disciplines. And as my selling point, what do I need? Patience. Nothing happens, Rome wasn't built in a day, that kind of stuff. Honestly, if a mathematician's work is somewhat well known by the time he dies, it's considered successful. I think part of that's a publication thing, but that's another discussion. Freedom. It's research. It's pure research. That means if you tell a mathematician exactly what they need to be working on, it's not research anymore. That's advanced development. Those two things. And cheap equipment. I can do a lot with a MacBook and a whiteboard and a whole lot of paper. I'm sorry, trees. That's really all we need. So, my thing kind of got messed up.
I actually have a lot of paper in my car.
Quick question.
Yes,
Yes.
but they're all McDonald's
Oh,
wrappers.
wow.
I'm kind of
No.
surprised in that I get the impression from you that you're not pleased with the amount of mathematics machine learning is bringing into companies.
What was your first clue?
Considering the fact that I've personally never seen as much math brought into a company by any other trend except for machine learning, I'm curious as to why you feel this way.
Well, I think that machine learning is really exposing the limits.
There are some great things about machine learning. In particular, I did actually write an article that, to avoid coming off as I hate all data scientists. There are, I'm going to call it like a certain layer of mathematics that was developed to allow these kinds of developments to happen. There is math in machine learning. What's ended up happening is that there's not enough of it to explain it. So the mathematics explains an algorithm, the mathematics explains a model, but what they aren't really talking about from a probabilistic standpoint are things like convergence, things like probabilistic foundations, all of that kind of stuff. A lot of the stuff, it becomes, I did enough math to create a tool, and then we stopped there because the business has got results.
And it's 70 years old. There is
For
no
me,
new math.
I've never seen any technology get pushed that's caused so many engineers to start going back and relearning calculus, linear algebra, and all
And
these
I
things.
appreciate
and the
that.
math push that I've seen in this is it's kind of and I understand that there's a lot of looseness to some of what's done that isn't as strict as what a mathematician would. There's a lot of jokes that go on about that, but I'm surprised that there isn't something encouraging for you about the passion for math that's being generated.
It's a double-edged sword on the passion part. The passion generates interest, but what ends up happening is passion also can become buzzwords because that's easier. It's easier to let passion turn into buzzwords once business people get a hold of the buzzwords. I bet the people who really like the research side of it and the engineering side of it are into mathematics, but they're not the ones driving the decisions anymore.
Yeah, and I understand where she's coming from, and if you look at the pattern of our technology over the past 60 years, when engineering curriculums came along, they were applied math and applied physics degrees. Nowadays, it's hard to find that.
Mm.
And so, you know,
They've
back
all,
in the
they've
80s.
all moved on to SpaceX.
Yeah, there was lots of research going on at IBM and Sparrows and all those places. They had scientists, they had mathematicians, they had engineers, they had everything there. But you look at the makeup of the average high-tech company today, and you may have a small handful
But don't you
of
think that's
those
a
folks.
maturity trend?
I think it's a maturity trend in certain technologies, but to innovate new technologies and where we need to go, we need that again. And what she's trying to say is we need to go back to basics, and we
Well-
need to go back and do that again.
There's room for both. I mean,
Yeah.
obviously you have to
Oh,
sell
yeah.
crap to be able to, like, I don't, you know, you have to sell stuff to be able to fund research. We need both.
Mhm.
My call is just that we've swung so far on the other side to make sure that, oh, well, let's cut costs as much as possible so that we can say that we did a great job this quarter. Little long-term thinking, that's really what I'm advocating here.
Well,
Yeah.
one of the reasons why we've lost the research and development for mathematics, I think, is because of the fact that the quarterly demands that she's talking about for business have meant that only the smaller companies are able to, or smaller specific companies are able to do the actual real innovation, and they get acquired or bought out. So I think that to this end, a small research firm or small mathematics firm can just follow that same model instead of being, really sponsored by the major companies. Maybe we just outsource to smaller companies for mathematics research.
I think it's,
And
I
that's
think, I
one
think the
thing.
problem throughout the industry, though. I mean, the
Yeah.
truth is, it's hard to do anything really significant under a 3-year ROI.
Yeah, and that's one nice thing
Or
about
three-quarter.
companies like, like Intel, for instance, because they take those small companies that Jay is talking about and they fund them for innovation. And so more companies need to do that and feed that. I know.
The downside, though, and while that's encouraging, what I've found in my own attempts at VC funding, admittedly small because I'm 28, because who's going to listen to me, right? It still boils down to a production cycle, right?
It
They
does.
want, and it's an attitude that I understand, but at the same time, at least would encourage to look past just the next quarter or year. And consider it. It's an idealistic pitch, and I get that.
And it's a
what R&D is
balance.
for.
Yeah,
It's a
but
balance.
It's a
that's
challenge at the
required.
top level too, though, right? It's you've got Google X and Microsoft Research, and they get yanked back and
Having
forth
Mhm.
too.
Yes,
So
and they get
It
laid
feels
off.
like they're trying to resolve problems and refine problems rather than solve new systemic problems.
Yes.
Well, that's because they have to keep going over and starting from scratch.
Yes.
Every time you let go of a bunch of mathematicians or serious research scientists, somebody new has to come in to fix the problem that they were trying to solve. Like, well, I don't understand what they were doing because they don't document very well, so I have to start over from the beginning.
Yeah.
Do not pass go, do not collect the $100.
Yeah.
So-
Unless it's like, the company I work for, that is a core part of the product, is how we handle things through mathematics and science. So those people are cherished because we wouldn't be able to make money off of our product if we didn't have those people.
But therein lies the problem, right? So when we start looking at, we in the industry, we start looking at mathematics, what her point is that math is not a product.
Mhm.
Math is a component for the product. It's the ingredients for making the cake. And I mean, we still have products that have multi-year life cycles in development, like ASICs, for example.
Yeah.
Right. So if we looked at ASIC development in mathematics, or even underneath the ASIC development, but in the same kind of vein, which is this is a 3 to 4 year, and maybe eventually it won't even come out because sometimes ASICs
Yeah,
don't
and that's the
actually
same
work.
as like processors. Yeah.
Right. But instead, people say, oh, machine learning, and I need to have a good machine learning product out next quarter. Give me the math.
Yeah.
It's like,
Yeah.
what
If you've,
Math on demand.
and if you've got a small company that is doing that level of actual math, how much are they putting back into the industry, into the community of that, and how much is being put into the product?
Yeah.
I completely understand that it has to go in the product because contributing to open source doesn't necessarily pay your salary
Right.
or keep the company going or keep bacon in the kitchen.
See,
It's
this
a balance.
This
Yeah.
is the big
It's a
difference in
balance.
how Bell Labs did work and how they advanced the field by doing innovation through research versus brute force iteration as we do today in most of our products.
But
Yeah, it was
software and
research
Why
hardware.
did they change? Right? They didn't change because people got bored. They didn't change because the researchers, left. They changed because the market put demands on that company that required them to have more replicatable, consistent small iteration results that didn't really allow for that level of research.
I think the market is just code for an attitude problem.
You know,
And there was the final.
and I think she's right about that,
Specifically,
because
Personality, but-
that's it, because it was the new leadership of AT&T that came in.
Yeah.
It wasn't necessarily market forces. It was the leadership of
Thank
the
you.
priorities.
Don't you think
'Cause
that
that's what I was about
the
to
way
say.
the way we evolved this, in that most companies, product managers expect to be deciding what features are going to go into products after negotiation with engineering. If you have features coming out of research, there's no control over it.
That's the beauty of it, though.
Predictability.
Mhm.
But that's not what the product management leadership of a company wants.
That's the
Right.
problem, though. That's why it, to me, it's not an economics problem. It's not a market problem. It's an attitude problem.
Yeah, and see, that's the neat thing about, for example, our CTO, the people that work for him are the product managers. So the product managers work for him along with the CTO's office.
So it sounds like it's not just a mathematics problem either. It's a basic science problem. We're not
I
doing
mean,
basic
chemists used to
science.
do tons of contributions
Yeah.
in industry
Yeah.
too. I switched out of chemistry because I wanted to go into materials chemistry. And then you look at it and go, yeah, industry they don't fundamentally. Now there's an expensive, right? I just need a computer and a whiteboard. Boy, you want to try to pitch like, please fund my chemistry project, right?
Need a lab.
Right?
Like perfume industry.
So, well,
Mm.
yeah. Anyway.
All right.
So she's on slide 4.
Moving forward.
All right. Basically, to kind of hammer this point home and to give you guys some actual technical content to play with, I'm going to go through some of my journey in mathematics. Some of this will be theoretical, the kind where a manager would look at it and say, why do you even bother? Because I don't see an immediate application, but I will try to explain why it needs to be done. And then some that are clearly applicable and some that have been applied and built out for real, just by taking a different approach. So this one I won't spend tons of time on. I did give a talk on this at SDC. So this one, the idea of drive failure is not a new problem. It's a saturated problem. Everybody's talking about it. It's boring. But what I ended up doing was taking a slightly different interpretable approach. So we looked at medium errors, which are just head issues on a drive. Sometimes they can have 1, sometimes they can have 10, sometimes they can have 150,000, although I swear that was an anomaly in the data set, but I couldn't throw it out. And so this is dead. All right, so what we can do, I'm sure Markov chains are fairly familiar to most people. They've kind of become a buzzword with people using the term without understanding it, but whatever. So here's some other. So what happens is each day data comes in, and it's going to return some kind of medium error count. I'll try to do like what my students used to complain about and not block the board because I'm left-handed. So each day, you'll either transition from your current state to another state or you'll stay there. And there's a probability associated with that. Probability of transitioning here, probability of transitioning here, probability of dying. The nice thing about this is that I can draw it out and you can see what's happening. You understand what this means. And this makes sense. Medium errors accumulate, they change with some probability, and then eventually everything dies. And when it dies, it stays dead. This probability is 1. So what I did was I just took that very simple thing on a single predictor. As it turns out, that actually outperformed almost every other model out there for drive failure. The other nice thing about this is the kind of thing that you can get out of this isn't a black box algorithm. It is a simple matrix that we can just collect them in. So it ends up being a diagonal matrix because things don't lose medium errors. It's just a matrix that comes out. That matrix has several major theorems associated with it that give you answers to questions. How long do you spend in transient states on average before you die? How long, what's your expected time to failure if you are at this state today? What is the probability that you will fail in the next 30 days, 90 days, whatever? Any of those questions, all of them are answered with one matrix. No retraining, nothing necessary. So what we ended up doing was building out a full monitoring system for data loss risk with full granularity. I can look at a customer, I can see his overall risk of data loss. I click on that customer, and it shows me all of his systems. Each one of those has a risk of data loss. Click on a system, I see every single enclosure. There's a risk of data loss for that. Click on the enclosure, and I see the probability of failure in the next whatever days he wanted to know for every single disk. basic probability. Simply because I got these probabilities in a nice, elegant way, I got to use essentially high school mathematics to build out this system. It runs every single day on tens of thousands of data domain systems, millions of disks every single day. And it actually, from our post hoc analysis, basically justifying analysis, actually does a really good job of fixing that. So it's a great way to rank your customers. So there's one that actually came into a product. You can prioritize customer support calls. So slightly mathematically boring, but there we go. All right.
Mathematically boring, but it works.
And it worked.
And
It
that's
worked
maybe
and it's
the more important
Things
interpretable.
that work are often boring.
So maybe there's a bad side to having a bunch of mathematicians. Maybe they want to make everything mathematically exciting.
There's
like
a
physicists.
pull back and forth with the let's find something that works while keeping it as simple and interpretable as possible. That will be half of my job, and that's fine. I'll build those things out. But honestly, of course, where my interest lies, something a little bit more like this. This one is the one that I would say a general manager would look at and go, why in the hell are you spending your time on this? And I will explain why. So this is my pet project, my little baby. This is kind of where we get to go a little technical, a little bit theoretical, and back to the notion of the looseness of machine learning. Actually, I can flip this over, can't I?
Nope.
Nope, just kidding. We won't flip it over. This eraser
It might
sucks.
flip over on you. You might wish you didn't flip it over. Yeah.
Well, this eraser sucks. Okay. So, quickly, independence probabilistically is pretty well defined, right? If I have two events, A and B, it's two events. They each have some probability of occurring. The A and B are independent. I'm trying to make my board writing nice and large. A and B are independent. Couple ways of saying it. If the probability of the two of them occurring at the same time is equal to the product of their individual probabilities of occurring, or if you're more of the Bayesian type, the probability of one event given that another event has occurred is the same as the probability of it occurring. In other words, this contains no information about A. That's the definition of independent. What is the definition of dependent? You can tell me correlated, that's linear. You can tell me mutual information, that's distributional. What is the probabilistic definition of dependent? For the last 100 or more than 100 years, the definition of dependent is simply not independent. It is defined as a negation of an existing definition. Why is this a problem? Most of the stuff you see in statistics requires something called independent and identically distributed random variables.
Yes.
Yeah.
So your central limit theorem, check out my Math Citadel for a post on that one. Your central limit theorem, most of your machine learning algorithms, your inference testing, drawing samples, all of them require independent and identically distributed samples. How often does that happen in reality?
Not very often.
How often are your features that you're trying to do regression on actually independent?
Never.
Almost never. Why do we still use these assumptions? Because the sum of independent random variables gives a nice distribution.
And the math is
All of the math is easy. You don't have to do convolutions. You get to use products of probabilities now. Convolutions are icky. I'm a mathematician, and I say convolutions are icky. Why is that the case? Because independent comes with qualities A, B, C, D, E, F, whatever. That means simply dependent just comes with not those qualities. If there's no formal definition of it, how can you know what it brings you? That is what I'm trying to change. So here, I actually did, and with the help of a co-researcher of mine, Jason Hathcock, because he actually came up with the idea, I just made it work. It started off with this notion from my PhD advisor that he actually just did it just on the way of inventing a way to generate random graphs. And then I don't think he really even understood what he did. But I looked at it and said, wait a minute, he actually created a formal notion of dependence. And there are some limitations. That's what happens when you create something brand new. You have to. So let's say, to keep it easy, we have a sequence of coin flips. So I'll do it out this way. So the first coin flipped, I'll call that epsilon 1, can either be right, heads or tails. And those have a certain probability associated with it. Right? All right, so the first one you flip it, you get one or the other. Now, if I'm going to create a sequence of these coin flips, if the coin flips are totally independent, so what is the probability of getting heads or tails, assuming that heads came up? If they're independent, what do you get? That's just P. That's just Q. Nothing's changed, right? Because the information contained here that this has occurred does not affect the next one.
Lost.
What if it did? What if it did, and we can formally define different notions of dependence? So what we introduce is something called a dependency coefficient. And this is a way to weight towards something that has already occurred. So we use a different notation. So this is how we do it. We define some
When
of
are we
these.
going to Vegas?
Well, this is the primary problem that people have when they go to Vegas, because they think that these things are dependent instead of independent.
Right.
Right.
Which
So
is why when you go to the roulette table, they show what numbers have come up like recently.
yeah.
Yeah, because
As
that's
if that-
totally going to help.
As if
yeah.
that, you know,
Yeah, like that's going to mean something.
Yeah.
Yeah.
like it's a Markov chain.
In a way, gambling's existence illustrates the lack of understanding of statistics.
oh, sure. The
Brilliant.
gambler's room problem is a wonderful example of application of continuous stochastics.
But we make this mistake in IT all the time too, right? I mean, we assume that this, because this failed, then that means this other one's going to fail, or because I've seen this happen before, that means something else, that
But they're
something's
not correlated.
Yeah.
Unless they're-
But sometimes they are.
Unless they're discs from the same
Yeah.
batch and they're all.
Well, exactly. Then we make that mistake too. So we look at two
Yes.
disks and we say, well, these are totally independent, but then we forget that we installed them on the same day and they came.
Or they
Then
have
there's
the
also
same
the
date
notion too of people throw around the word correlated dependent. Those aren't exactly mathematically the same. Correlation is a linear measure of association. It's not just a measure of association. Mutual information is a measure of the information contained in one probability distribution inside of another. Distribution is not probabilistic. There's levels of that. There's the idea of probabilistic, distributional, which is weaker, and then linear association, which is more geometric, which is even weaker than that. Nobody until now has actually gone all the way down and created a formal notion of what it means to be dependent. So if we have this level of dependence, and now let's say it is affected by the first one. So I'm going to weight in favor of the outcome. Oh, that's a plus. The outcome of the previous one. So if a 0 came up, I'm going to weight in favor of that. If a 1 came up, I'm going to weight in favor of that. The reason that we basically adjust this way is to make sure these probabilities still sum to 1, because we can't break math in creating new math. Not okay. Okay, so here's just kind of a way to look at this. If this delta is 0, everything's back to normal, we're independent. If the dependency is 1, so if this is 1, p plus q is 1, p minus p is 0, that means everything is totally deterministic. Now, and you have this concept of everything in between now. So now I can create sequences of dependent random variables. Now the third one, now we can get some stuff that's kind of interesting. This is kind of where I took some stuff and went a little crazy, which is actually, I'll give you what you see here. These are graphs that are dependency structures generated by a certain class of functions that I have created. So the third one, should it depend on the second one directly, or the first one directly, or something else? If it depends on the first one directly, you're going to get a dependency graph that looks like that. It all depends on the first one. In other words, it doesn't know what happened to the second one. It doesn't care. There's some implicit information contained, but it goes straight back to the first one. That's what my advisor did. Great for random graph generation, actually. Not so great for other practical stuff, because chances are, if you're on the line and you're going to make a decision about lunch, you're probably going to look at what the person in front of you did. That's this one. This is sequential dependence. So in other words, what this means in practice is that I will weight in favor of the previous one. So this is Q minus. Now this one, even though the first one came out of heads, this one came out of tails. So I'm going to weight in favor of the previous one, and so forth. Then we can get kind of crazy because I'm a mathematician and I like to generalize things. So the nice thing about this, though, is this isn't just for Bernoulli random variables. I've done it for categorical random variables as well. I can do it for any function that generates these dependency structures, as long as it meets a very general set of requirements. The other thing that it guarantees with this class is that I can create a sequence of identically distributed. So in other words, the probability that this guy comes out 0 just in general is the same as this one, but now they're dependent. So all the stuff that you used to be able to get, oh, we need independent and identically distributed. I've got identically distributed now, and now it's dependent. What does that lead to? 4 new probability distributions. Generalized versions. A generalized binomial distribution, counting the number of heads, but now when they're dependent.
Causes gravity.
A generalized multinomial distribution. Same thing, but for categorical random variables, more than 2 categories. A generalized geometric distribution, counting the number of flips until you get a head, a success. That one actually doesn't care about the dependency structure at all. It is always, literally doesn't care. All you need to know is that and the probability of success. A generalized negative binomial distribution. These are all extensions of very, very common probability distributions. I'm hoping to apply these to things like dropout and determinant and testing nodes for neural networks. All sorts of other things like that. So at first when I started it, I have to admit my management looked at it and go, what are you doing? Just work with me here, like let me try this. I'm still looking for other potential applications, but probabilistically, these kinds of foundations, because what are extensions? We can move into continuous space, right? Now we can get generalized normal distributions, generalized beta distributions, generalized gamma distributions by moving into continuous space. Working on it, it's not as easy as it sounds. So the idea is if you define independence and then dependence is simply not something else, and then base the entire field of statistics on dealing with independent stuff, right? All of your inference testing, we work with that because the math is easier. What if you actually rebuilt this from the ground up with a notion of dependence, in which case independence becomes simply a special case? You can rebuild statistical inference this way. Long goals, I will probably die before it finishes, but hopefully I'm not the only one that decides to work on this. All right.
Just the implications for storage alone.
What kind of implications do you see? Because I'm always looking for feedback.
Well, I mean, your other work on risk modeling, for the failure rates is the obvious one, but that in turn has profound implications for what Curtis does with backup and recovery and possibilities of restoration failures and those kinds of things. If the actual source of where the dependency is has that wild a difference between in the outcome, I mean, we're talking about entering into chaos theory and complex adaptive systems.
That was
and
actually
autopoiesis.
suggested to me on Sharkovsky ordering and chaos theory. I haven't been able to make that one work yet.
Well, where the question would therefore come up is, at what point in time do we start injecting turbulence into the system? And that's where the chaos theory really starts to take hold. And what I see in your situation is that the actual placement of the source, like trying to model weather patterns, for example, where you determine your actual source starting point can have radically different outcomes just based on minor variable changes.
That's what I'm hoping will happen when I start to move to, because right now you see just discrete space here, and the probabilities are discrete, like P and Q or P1 through PK, right? This isn't like a distribution where it's a continuous distribution. That kind of application I see happening, when I can base. So that's generally the way mathematical development works. You start discrete, just like calculus. You started with sums, you took the limit as the distance went to 0, you got integrals. I'm trying to do the same thing here and always looking for possible directions. And I wonder too if, I hadn't thought of that because that's an interesting notion of how to use this.
Well, when you start going through the iterative process of this, and right now you're talking about linear systems, but what if we're talking about nonlinear systems? And those then you start to iterate through these mathematical constructs with a nonlinear entity such as storage. And over time, we'll see an autopoiesis of, a self-emergence of a pattern of behavior, and it will be radically different depending upon which, basic assumptions are talked about. Those assumptions, by the way, are ignored, to your earlier point, in the current data science machine learning problems.
Because they have to be right now.
Right. Well, they make the assumption, right? They assume a can opener, to the old physics joke. They assume a convenient, or more to the point, they assume a frictionless environment in data learning and machine learning. And you're pointing out that this is not a frictionless environment. Your black box starting point is not always going to be the same.
The spherical
Now,
cow.
something's like kind of
Yes.
dawning into this whole process. What problem are you trying to solve when you started diving into all this?
So interestingly enough, I really just read my advisor's paper because he did it just for Bernoulli random variables. The first thing I did said, why not categorical ones, right? It's a natural extension. Bernoulli is 2 categories, categorical is more than 2. So he's like, I never thought of that. Now let's just see if it works. Actually, with a whole lot of really ugly arithmetic and a lot of wasted paper, the extension was actually pretty natural to come up with something similar. I stuck with the same dependency structure. Then the next thing was looking at, yeah, that's a really nice, it's a nice result, but there's got to be different kinds of dependency structures. This one seems really limiting.
But there wasn't like a problem somewhere
No.
that you were trying to solve.
It was just a what happens if this.
So I think this is part of the hang up, is that the whole build it and they will come idea, we tried really hard in like the late 90s and it didn't go well, right? And so I think now there's a huge push to have very discrete, very well identified goals and problem sets that you're trying to address before you dive into that research side. Whereas, what you're talking about is more, you're diving into research based on your interests and your skill sets and what you think is, and then once you actually have something interesting, you're going out and trying to find
That's true.
a place to match it.
However, I'm not asking for one or the other. I'm asking to bring back the other bit that was abandoned. We already have here's the well-defined problem, please work on solving that, but we've lost the other part of it. We need both.
And historically speaking, a lot of the innovations that we have in
Accidents.
modern technologies were accidents.
Yeah.
because they were trying to solve a different problem.
Right.
Mhm.
But rarely, like, I'm playing with this and look what I found and let's go do something with it. I
Well,
mean,
that's true,
Let's
but
go
I mean,
startup.
that's
I ran several startups into the ground doing that. So
Yeah.
well, but think about it. So think about the people that we really admire through history and how they've actually done it. There was a lot of it. Tesla, and Edison. No matter what you think about the two of those guys, Benjamin Franklin, James Watt. Those people who were doing it based this way. And some of the greatest innovations that we use on a practical basis were not starting off by anything other than, hey, I wonder what happens if I do this. And
I spend most of my private time studying quantum physics. I'm all about like random pure research.
He's my
What
new
I'm
best
saying
friend.
is that capitalistic societies, I'm not sure actually support that model anymore.
well, I don't know if it has to do
But
with
they
being-
should change. Like, if you think about the
They
world,
should change.
and we go back a little bit, you can now understand the difference between independence and dependence. Why is the world functioning on independence only? Right?
'Cause
Why
you
are we
didn't-
doing this? There's a field of math and physics that we're simply ignoring,
Yeah.
and technology.
And quantum mechanics supports
The
all that.
world
Yeah.
is a set of fortunate or unfortunate events that are dependent. Yet we can't link them together because we don't have a way to describe them with language
if
or
I'm,
math.
if I'm a product manager and I have to plan out my roadmap for X number of quarters, like how does that become relevant to me?
Well, that
That's-
doesn't excuse the ignorance of a product manager.
Right,
Right,
so to be positive on this, that's where I go back to we're cheap and you don't need many of us. Like, this is my example
Because
of
there
this
aren't
is,
that many of you.
well, unlike a chemistry lab that, I would have to come to you and require significant, chemistry, like that lab equipment is expensive. And I get it from a project manager standpoint, like that is a massive financial risk to take.
That's not here's the problem.
This kind of stuff, even from a capitalistic perspective, to go to project manager is just kind of take a risk a little bit, and with such a small amount of your budget.
But I think part of the problem is that you're mapping on two different things incorrectly, and one is the actual operational building of a product, and the other is the technology research that would therefore be used as the ingredients to build that product.
Right.
If I were a CTO of a company with these two options, I would put those two things as far apart as possible. Because most product managers are not more than spreadsheet jockeys. I mean, being a product manager, I put myself into a very interesting category there. And I'm not a very good spreadsheet person, which is why I'm not a product manager anymore. Really good product managers have an understanding and a feel for what's going on around them so that they can actually have a vision of where they
But
want things
don't
to
you
go.
agree that the actual difficulty in executing what you just said is the reason why Google X and Building 8 and those institutions are physically separate?
That's right.
Mhm.
That's
Yes.
right. And that's why. And in fact, this is not a product management problem. this is a management problem.
Yes.
Right? And
Right.
so it's going to take somebody above a product manager or a director of product management, for instance, to say, I know that my CTO's office is doing this kind of work and I can see the applicability.
Well,
right?
I can go into one that was inspired by a practical problem, although you did see that talk already, so you'll have to bear with me.
But one last point is that I've been in situations where we actually did get the room to do research, and there were no ties, there was no deadlines put and so forth, until the company hit a rough quarter,
Yeah.
right?
Yep.
And then suddenly it's like, well, what are you guys producing? Like where's the ROI and so forth? And
Yeah.
so there's you end up in this risk model that it's not good for the imagination, right?
Well, and I think that's where a lot of companies are really short-sighted because
Fair.
the problem winds up being is that you have the timeline of development actually goes from yesterday to tomorrow, not just today. And the thing is that you have to have a certain amount of budget for maintaining existing products. You have to have a certain amount of budget for updating products. You have to have a certain amount of money budgeted aside for existing products in development. And then you should have another amount of money for longer term visions that quite may not, we call that risk money, right? And the problem is that we kind of,
Moonshots.
sorry?
Moonshots.
Moonshots, right? So what the problem I've seen in the management stuff is that they basically budget backwards in time, right? So when they reduce the futures.
Yes.
They're basically borrowing from the future to pay off the
I'm
promises they made
intimately
yesterday.
aware of that.
And then eventually cut themselves off at the knees because now they have, since they, desecrated their future, now they're stuck.
And then you get Blockbuster versus Netflix.
Yes, there you go.
An example from history, a very old company with 3 letters, IBM, right? They are actually not a single company as you might think. They're 2 separate companies. There's IBM, the business side, and there's IBM, the research side.
Yep.
And they're
Same
very
with-
different
same with
companies.
Intel.
Yep,
Same
Intel
with-
Labs. Yeah.
Exactly. So these guys have something going right in that respect
But a
at the top.
company has to reach a size and have
Yeah.
a certain
That's-
amount of
that is
funds
that's
to
very
afford
true.
and
You need to have a
afford.
buffer.
But
That's a
Intel
luxury.
started out that way, so, but
And so
they
we're back to breaking the model again.
Yeah.
So realistically, you were talking about the capitalistic thing. I think part of the problem is that we don't have an awful lot of mathematicians who are good business people, and as a result, they want to have a purity
A lot
in
of people
business
get
that they have in
degrees
math.
because they're bad at math.
What's that?
I said a lot of people go into business because they're bad at math.
Right.
Yeah.
So the problem is you don't find an awful lot of mathematics startups because they want to have a purity in business that they get in math, and it's just not going to happen. In fact, it's probably a variance of about 7%, not 97%.
Yeah. Unless
So-
you find a way to productize your math.
Fast.
Yes.
Yep.
All right.
So, what about looking at one that was actually, we'll say, practically inspired, but still led to pretty good theoretical developments? So, this one was actually a lot of work on my dissertation. Actually, it is similar title to my dissertation. And I did give a talk on this one, so John will have to bear with me because he's already sat through this. You've already seen this guy. So, a couple of things we can look at, and where's my marker? All right, so, and I say server, realizing you're all IT people, and don't read too much into the notion of literal server. I mean just, say, an entity that can complete tasks or jobs. But in queuing theory, we call it a server. So it's loaded language. Okay, so that's what you have, some kind of server. And into that server, at some arrival rate, some X number of jobs coming in, from outside to the checkout counter per unit time, or sometimes that rate can vary, I allow that. These are jobs coming in, so these are people coming in that want something done. They come in randomly, according to what I assume is a non-homogeneous Poisson process, which is a fairly general version of a Poisson process. The reason people use Poisson process to make what's called an MM1Q is, again, the math is easy. Queuing theory gets really rough when you don't have that memory list property. So you can actually relax that just a little bit and let that arrival rate vary through time. That's going to come into the actual server, and nobody gets served in the exact same amount of time. Now, even when you're at the grocery counter, 2 people with 3 items each aren't going to be checked out in the same amount of time. It's random. This is called its service distribution. It's got some amount of time that it can serve and the probability that it will take that amount of time, and then when the job's done, then they come out. All right, so the paper that I read at first actually just did exactly this by relaxing the notion that it had to be constant arrival rate. What they didn't do was, what they did do was assume that each job brought some random amount of, or an amount of stress, right? If you're gonna hit a database, you're gonna stress the server out a little bit more, right, than if it's just sitting there idle. They assumed all that's constant, not really mirroring reality. So I generalized that. What if each job that comes in hits the server with a different amount of stress? So what you see there that are not, that's called a hazard function. That's the baseline hazard function, and that's simply the rate of failures per unit time. That's loosely defined that way. I drew it as a constant because it makes my graph easier. I kind of got heckled about that at SDC. It's a constant.
Yeah,
it doesn't
who
have
did
to.
that?
It doesn't have to be a constant. Doesn't have to be a constant. But each one of these is going to bring a random stress. And so as long as it's being served or processed, the failure rate, the random failure rate process, will be increased by that random amount until the job is complete. So if you have 2 jobs coming in and the third one comes in before the second one is finished, that's how much you've increased the stress. All right, so that's the model. I promised I wouldn't throw too many equations up. The importance here is more just understanding the system. So the randomness had never been done. That was the first part of my dissertation. What's cool about that is that I can tell you the exact closed form of the survival function under the most general conditions. Well, there are still more generalizability because it's math and you can always generalize. That's called category theory, and I don't go there. No, even I stop somewhere when it comes to pure math, and I stop at category theory.
Quick question for those who may be watching the video and those of us in the room who are too embarrassed to ask. Can you define closed form, please?
So closed form basically means that I can write an equation that describes it. So when you say something that's not closed form, sometimes people call an algorithm closed form, like a procedural thing. But closed form essentially means I can write an equation as opposed to, for instance, it's difficult to write an equation for a space filling curve.
For what? I'm sorry.
A space filling curve. It's a one-dimensional. It's a one-dimensional function that can fill 2-dimensional space. Write that equation down. A little harder. Closed form means that I can write it down, and that it is, like in this case, it's a actually very nice continuous function. So the form isn't really important. In fact, it's really not that illuminating because the arrival rate can vary through time. I don't know what it is. The jobs are randomly arriving. The service time distribution is any one that you want. The stress distribution, if it's random, right? They're all getting pulled from some distribution. I do assume IID, obvious generalization, yes, working on it.
IID?
Independent and identically distributed. That independence actually does run through here, again, to make the math easier, although it doesn't look like it if you read the
That's
one
the
of
thing that forces us to munge our data to fit it to the algorithms.
Yes.
Is this what we sound like when we talk to non-storage people?
Yes.
Yes,
Oh.
yes, it is.
I think so.
Excellent
Yes.
point.
Yes.
Server.
Yes, you need a math background. Yeah.
It doesn't even matter if that distribution of your stress is continuous, discrete, or if you even know what it is, I can still write that equation down. Why does that matter? Because it is possible to get an exact form of the probability that your server under workload will survive past a certain time t without machine learning, training, any of that. It's an analytic form, also a closed form, another word. It's elegant.
It's a faster way to do something we do by brute force today.
Yes. Now, the catch of that is I have actually tried to see if this is tractable. There's a difference between closed form and tractable. Under the simple case, that integral that you see in that, that exponent will have to be numerically evaluated, even for fairly small cases. But numerical evaluation of integration is a lot better than just black box algorithms. Okay, what else did I do with it? How much time do I have left?
Not so much.
Not so much. How much is not so much?
5-10 minutes.
Okay, so a couple of different things. If you want to read my thesis, you can. But a couple of things I did some twists on it. What happens when you try to deal with load balancing? That would be an example of a not closed form. I can't get the closed form for that one. I can't prove that I can't get the closed form, but I haven't been able to get it. The best I think I can do is a conditional form with estimates. I tried really hard. I wasted like 6 months trying that. Again, back to the patience. 6 months I tried this. I learned a lot about strange things in combinatorics with all sorts of weird things trying it. I looked at something called a clustered task server, which I did talk about in the last Storage Developers Conference. That's what happens. It actually turns out to be a special case of this one. That's what happens when you assume that your server can be partitioned to accomplish different tasks. And this is actually where that dependent and independent random variable stuff came in. I did actually use it in my thesis. Because if a job comes in and a job consists of selecting, say, some number of these tasks to complete, the job is completed when the last of these 2 bits, right? You get your burger and your fries. You have to make them both, and maybe 2 separate people are making them. What happens if these selection probabilities are independent? What happens if they are not? That's actually where I did invoke that notion of dependence. Not the really general stuff I did, that came later, but I did actually invoke that. It was used. And it actually was shown to be actually a special case of that formula in a much nicer form. The other thing I did was look at reliability networks of them. And I use networks in a very, again, a loaded sense. I don't mean it literally a physical network. I mean what's called a reliability topology. Because you want to, the whole goal of this is to determine when your server might fail when it's under workload. What happens if, now this is a system, let's just call it a parallel system. They may not literally be in parallel, but I mean that there's some overall system that requires 2 of these server components, and if one of them fails, the whole system still can operate. That's what I mean. So I don't mean like literal physical, I just want to be fairly clear. All right, so what's nice about this is you can write a nice structure function, whether it's on or off, and it actually is pretty simple. If you plug in a state vector, I can tell you whether the whole system is on or off. I can do the same thing if I replace simply the state vector from basic reliability theory with that survival function. I can now tell you the probability of survival for the entire network. Not just for parallel, not just for series, but for any topology that you can create, because there's actually a really nice theorem from basic reliability that every reliability system is composed of either a parallel system of series subsystems or a series system of parallel subsystems. If I can do it for this, I can do it for anyone you want. I can tell you the probability of survival for a system built of servers just like that for any one that you can come up with. It doesn't matter if the traffic comes from outside to each node individually. It doesn't matter if that traffic is correlated. I can still do it. That was kind of the other bit I did. So why do I actually bring all that up? Because again, it's not a math talk, and my dissertation committee sat through a whole lot of time with me going into the really deep stuff on it. Because I think mathematics is worth the investment. I got a lot of really good feedback from the Storage Developers Conference presenting exactly that stuff. Good stuff for applications, good stuff for possible generalizations, good stuff for generalizing in a way that does mirror reality, which is kind of ultimately a mathematician's goal. We're trying to explain reality. It's worth the investment. Sometimes it's really theoretical and you're not sure if it's going to pay off. Sometimes it's got clear applied inspirations, but you still need the patience to develop the theory. Sometimes it's just as easy as the project Risky Business, and it's simple math that you just build out in a different way. I did all those things. All this stuff I did in the span of 3 years. One person, I am not the smartest person I know, like believe me. So if I can do that with like this much resources in 3 years, and 2 of them were funded at poverty level wages by my university, then that's how little you need to make some potentially really good developments. That's my plea, is just it's worth the investment, and it just takes so little for all the stuff that you can possibly create just by changing the attitude again.
Before you move on, that is the summary shot right there.
I did that on purpose.
Yeah.
Yeah.
No, that's great.
Okay, I see. So we're not that clever. There we go. Mathematics is worth the investment.
Yes.
Almost make you think the only way to really solve this problem is to fundamentally change how math's taught at a very young level.
That,
I couldn't hear you.
So the
No.
only real way to fix this problem,
I
at a
agree
grand
with
scale,
you.
is to fundamentally change the way math's
There was a
taught
really,
at a very young level.
there was a really sad, literally heartbreaking for someone like me article that came out. It was a political scientist who said that math is the Seinfeld of education. It's worthless. It means nothing. So here's the problem. Obviously, people in technology know that's not true. But that's actually a pretty small subset of people. And even then, those technology people still, at a fundamental level, believe that. They believe pure math isn't, oh, we've invented plenty. We can do plenty with what's invented. And if you take away that teaching of it, like, don't blame bad teaching and bad curriculum on a good subject. It's not math's fault that you can't teach it well. It's not math's fault that you don't let people play with it instead of just putting them through rote memorization work. I've tutored high school, anywhere from middle school all the way up. I've taught at university level for 5 years. I took people that hated statistics, and by the end they liked it, and they were nursing majors.
But the same notion, it's not anyone's fault who's in the workforce today that they have the opinions and background in math they
No.
do if it's derived from the way. I mean, in my entire academic career, I had one good math teacher. I had one great math teacher, and he was actually my physics teacher.
Yeah, I
Well,
had
yeah.
great math and physics teachers. They were wonderful.
But you're right, yeah, it's an attitude thing,
It
and it
is.
starts from children. Children who are scared of math, children who think math is a chore, grow up to be businessmen who don't value it.
Yeah.
It's an attitude problem, and you're right, it's not a capitalist problem, it's an attitude problem. And you can say it's in management, but it really is. Like, for a long-term change, it's back there.
Yeah, because like
And
my first great math teacher was in 6th grade. He's, one of the reasons why I stuck
The
with
one
it
who
so
lets you
much.
play with tangrams, the
Yeah.
one, like, instead of putting a worksheet, because, right, it's a sport.
He was the hippie math teacher.
You still have to shoot your hoops to practice, but at the same time, you have to let them actually play with it and have some fun with it too. You need both.
But you're the exception, not the norm.
Yeah,
Yes,
that's
and
true.
that's
I taught a
unfortunate.
lot of
It's
university
It's
students.
terrifying.
Yeah, it is. It really is.
And the way that math is taught in lower grades right now with Common Core, it's a joke. It's absolutely. And I know you're going to disagree with me on that.
No, I was going to say, I
but
would
it's a-
actually,
it's a freaking joke.
It's actually really funny because I've been having this debate. I have a 2-year-old daughter now. I've been having this debate with a lot of my family members who have older kids, and I actually think Common Core is actually an interesting approach to try to solve the problem, because the problem I always have with mathematics is I would always ask why, and no one could tell me. Nobody could tell me. The limited amount of Common Core mathematics I've looked at actually seems to be trying to get you to think of the why, and
Yeah.
not just
The why, or at
not
least
not
the how.
just the math.
I'll just
not
raise a
the
point of interest.
calculator.
Common Core is not a curriculum.
Fair enough.
It's a
There
set of
are-
standards.
There are curriculums targeted at it.
Yes.
And as with any technology product, you can deploy it well or you can deploy it terribly. And you can do them both at the same time.
Yes, you can.
Same buzzwords. Same buzzwords.
Oh,
Well,
yeah.
we do have to wrap.
No, that's fine. I think like I said, the talk wasn't meant to be more of a mathematical seminar. I wasn't going to put you guys through that.
That's the next one, right?
If you're interested, I am one of those people that like is almost starved for somebody that actually cares. So be careful what you ask for. Be very careful what you ask for. I try to channel that to the Math Citadel by writing some stuff, done things on examples of sequences of random variables that do not follow the central limit theorem. I've done some stuff on abstract algebra, a little bit of basics, just to kind of help. The goal is to actually reach those adults that kind of look back and wish they had done more in math, but then look at, say an algebra book, like an abstract algebra book, and go, what? No. Because I'll say it, we suck at writing for a general audience, taking more advanced concepts and trying to actually make you guys care. There's formality, and among ourselves, as mathematicians, we're going to be formal. I'm going to make sure that you use the right notation, the right implication, all that. But for the most part, to get the rest of you interested, especially adults now, if I'm going to prove something for you, if I make it too formal, you're not going to care, and you're honestly, no one likes to feel stupid. You're not stupid. You know more math than you think, but no one likes to feel that way, and we're kind of bad about not making you feel that way. I try to write some stuff in a more casual way while still maintaining that rigor.
And I guess everybody in the room
and that's a
is that
talent
way.
in itself.
Yeah.
Yeah.
I'll let you evaluate it if you get bored on your flight home and read some of the posts I put up.
All right. Cool. Well, we do have to wrap. Thank you very
Thanks.
much.
Thank you so much.
Thank you.